Hi, this video we're going to look at some examples of a moment, particularly it's in two-dimensional. A quick review, we're talking about moment of a force regarding a point. It's a vector, so the magnitude is force times moment of arm, and the moment of arm is going to be the perpendicular distance from the rotational point to the force. And for the direction of the moment, if it is counterclockwise rotation, that's positive. Clockwise is going to be negative. Okay, so knowing that, let's go ahead and solve some problems. So first example I want to ask is, for example, this horizontal force F4 rotating about Q. So what you're looking at, it's a grid, and each of those length is 1, okay? So it's 1 meter. And then you have a lot of this red arrow, that's the force, and the magnitude is labeled next to it. And the point of application, for example, this F4, is applied at K, right? Okay, so how do we solve this F4? Find where that is, rotating about Q, find where that is, right? So using this review we just had, it's going to be the force 2333. And this force is all in Newton, okay? Then times the moment of arm. How do we draw the moment of arm? It's from this rotational point to Q, because this F4 is rotating about Q, to this force perpendicular. So that's going to be the green is going to be our moment of arm, which happened to be 2 meter. Now let's thinking about the direction or rotation. So this force is going to rotating about Q, and what rotation is that? That's counterclockwise, right? So that's going to be positive value. Then we have an answer for that, 466 Newton meter. All right, that's our example 1. Now let's look at a few more. And now let's look at a vertical force, which we have here, F2. And let's make F2 rotating about D. Okay. Again, definition is force, which is 1688, times moment of arm. Moment of arm, it's rotating about D. We're going to feel free to extend this force and draw from D to this force, and the perpendicular will have to be this length, right? And let's count across 1, 2, 3, 4, 5. So that's times 5 meter. The next step is critical. You have to think about the direction, right? Is this force going to rotate around this point? What rotation? If you look at this, it's going to be counterclockwise. So that's going to be positive. So let's see. Is that right? Okay. So that's going to be our moment for F2 rotating about D. All right, so now let's look at those two problems we just did. F4 is being horizontal force, right? Well, F4, if it is horizontal, and you notice the moment of arm, this 2 meter, happen to be reading in vertical location, because it have to be perpendicular, right? Now let's look at F2. F2 forces being vertical, and you notice the moment of arm happen to be horizontal. So that's a little trick, a little pattern. If the force is vertical, direction, and the moment of arm will be horizontal, vice versa. Okay. All right, now let's look at some other examples. And instead of perfect horizontal or perfect vertical force, how about we look at a slanted force? And I see here there's F3, right? So moment of F3, that's 40 degrees there, rotating about P. How about that? Okay, so that's going to bring up to a different technique here. You have F3, which is slanted, rotating about B. If we're going to use force times moment of arm, let's explore that. So if I were to draw a perpendicular distance from P to this force, first I extend that F3, and then I'm going to draw that force. Would be something like there, right? But can I find the distance very easily? Can I find exactly how long that is? It's probably challenging because I really don't know that much geometry here. So in that situation, we know this route is probably cumbersome. You might be able to, but it's not that easy. So in order to do that, we're going to introduce a brand new technique to deal with this force is slanted. First, what we're going to do, step 1, we're going to decompose. Just like how you decompose any other force. So remember, we can extrapolate F3 out. We're going to decompose to X direction and Y direction. And here, I only worry about the magnitude, okay? So this X direction, the magnitude is 1000, and this angle is 40, and it's adjacent, so times cosine 40. And for this Y direction will be sine 40, right? Because you used the cosine already, and also it's opposite of 40, so it's going to be F3Y, it's going to be 1000 times sine 40. That's our first step. Now move on to the next. Then we are going to solve this moment of this X component rotating about P. Can we do that? Yes, because this X component is perfect, horizontal, which we have been doing for the first example and the second example. We can do this type of problem. And also, can we do force at Y direction rotating about P? Yes, we can, right? Again, it's perfect horizontal problem or perfect vertical problem, rotating about point. Yes, we can. So that's where we're going. Now let's solve the first one. For this F3x, it's 1000 times cosine 40. So that's going to be our force. And we're going to think about what? Moment of arm, because force times moment of arm. And now let's think about it. X direction is right here for this force, right? Y direction is right here. For this X direction, and we're rotating about where? Point P. Point P is right here. And now only want you to focus on this X direction. And what do? This force is X direction, so the moment of arm have to be vertical direction. And again, you are likely going to extend this force to this direction. And we're drawing, using the grain, drawing our moment of arm. That's from P to this F3X. That's going to be our moment of arm, and it happened to be vertical. So we're right. So it's 1, 2, 3. So times 3 foot, 3 meter. Again, don't forget the last step here. We have to figure out the direction, right? Is this force here rotating about P? What rotation? So this force is going this direction and rotating about P. It's going to be clockwise rotation. So that's going to give us negative. Super important. And then you can go ahead and find this answer here. So that will give us the value of negative 2298 as integer. round up to be this, and it's going to be Newton meter. All right, now we are going to solve. This is F3 x direction, rotating about P, right? So we're going to do the same thing for y component, rotating about P. So y component force is 1000 times sine 40 right here. Then, so which means this force right here. And we're rotating about P and have to draw moment of arm. Moment of arm is going to be perpendicular distance from P to this force. So that's our moment of arm. And that happened to be 1, right? And now let's think about direction. This force is going to rotating about P. So if you will think about that, this force is rotating about P by rotation counterclockwise. So that's going to be positive. So putting the calculator 1000 times sine 40, you got 640, around 643. I'm just rounding out for this problem. Newton meter. And okay. Then what's going to be our next step to solve this force that's slanted? You figure out both x force and y component force. Can we add them together? Yes, because you already considered the direction. If you get a negative direction, that means negative z-axis, right? And when you get positive, which means the direction is pointing to the positive z-axis. Then when you have the same dimension, when you have the same direction, of course, we can add those two vectors together. They're the same, they are all on the z-axis. So you can add them. And so the very last step is, if we were trying to solve this F3 rotating about P, we're ready to get an answer. So it's going to be this value, negative 2298, then plus 643. Add those values together and let's see what we have. We'll have answer as negative 1655 Newton meter. Then that's your answer for this M3 rotating about P. Hopefully this helps to look at how you solve a problem which is slanted. How do you define it? You first decompose, then you look at each horizontal force rotating about point and vertical force rotating about point, and thinking about the direction. Then you add them together. The reason you can add them together because they are all on the z-axis. Okay, whether it's pointing to the forward or backward, positive or negative direction, but they are on the z-axis. That's how. Okay, now let's look at another example. So every single example here have its own unique feature, and all those are something you want to master. Now let's take a look. If this is going to be the force F4, F4 is right here, right? And if we are trying to have F4 rotating about J, J is right here. What's going to be the moment? What's the uniqueness of this problem is this F4 is going through this point J. Extended F4, so J is on the line of action of 4. So that if we were trying to take it out, this is my J, this is my F4. Well, using force times the moment of arm, force is 2333. What's moment of arm? If you were extend this force, okay, and you were to draw from rotational point perpendicular to this force, which is right down here, what is moment of arm? Moment of arm is 0. So in that situation, you have force times moment of arm, that's going to be equal to 0. One thing you notice this is if rotational point J is on the force goes through the force, then you are going to get moment as 0. Think about it. If you are trying to open the door right here, right, and you have a force, this is the hinge, you have pushing in there, does it even turn? You won't, right? If you have a force just going through the point of rotation, it's not going to rotate. So that's moment is equal to 0. All right. Now let's look at another example. Let's see, what do we have? How about if we do this F1 here? You notice this F1 has something different. F1 is not given in an angle. It's given in this geometry 3, 4. Okay, so we have this F1. If we have this F1 rotating about D, D is right here, F1. How do we solve that? F1 first is slanted, so we're going to use the same thing we did for this example 3. We're going to decompose. So let's take out the F1 out, and F1 is equal to 2000. We don't know the angle, however we do know this geometry is 3, 4. Earlier, I think there was one example we talking about. You can go ahead and find the angle using inverse tangent 3 over 4. And then you can go ahead decompose to x and a y. You can, but there should be an easier way to do that. And here I want to just thinking about this common right triangle. If we have a 3 and a 4, what's going to be hypotenuse? It's going to be 5, right? Because 3 squared for right triangle, Pythagorean theorem, that's 16 and 9, and that's going to be 25, so that's going to be 5 squared. So 3, 4, 5 triangle will become our friends through the statics and strength material. Okay, and now let's look at some other typical right triangle that helps us a lot. How about if I have 30 and 40? Would that be just proportional? Everything scale of 10, so that'd be 50. All right. So if there's a problem, they give you a dimension 30, 40, then you said, okay, that's 3, 4, 5 triangle. I don't need to use a big number. I scale down. And if another problem is giving us, for example, 16 and 12, is that 3, 4, 5 triangle? Yes, I don't even need to solve this hypotenuse because I'm going to scale down. So that becomes 3, this becomes 4 because they divided by 4, right? So that's a 3, 4, 5 triangle. Now let's look at some other things. And let's look at this. If this is 5, this is 12. What would the hypotenuse be? 5 squared plus 12 squared. So it's 25 plus 144. That's 169. 169 happened to be, that's right, 13 squared. So this is going to be 5, 12, 13 triangle. That's another one we will be using. So 3, 4, 5 triangle and 5, 12, 13 triangle. Right? So knowing those typical right triangles 3, 4, 5 and 5, 12, 13, it helps us for the future problem. Now let's go back to this one. F1 rotating about D. F1 rotating about D. All right, if I were taking out F1, and we know the magnitude is 2000. We also know it's 3, 4, 5 triangle, 3 being at the vertical, 4 horizontal. So first we're going to decompose to x direction and y direction. So F1x is going to be using 4 because that's horizontal, 4/5 hypotenuse times 2000. That gives us 1600 Newton. And now let's look at F1 y direction. That's going to be 2000. And our y is 3, so it's 3/5. And that will give us 1200 Newton. Some of you might think, I think we're going to add a negative because this is going downward. I agree, this force is negative direction. But here, remember, our goal is trying to find a moment. And moments have its own sense of direction, right? It's counterclockwise rotation that's positive. Clockwise rotation is negative. So we really don't care this force is going what direction. All we care is how this force is rotating about that point, what rotation that is. So in that situation, the force direction here shouldn't be a concern, okay? Because ultimately decision is the rotation. Knowing that, now we decomposed. That's our first step. The second step is we're going to solve this x component rotating about d. Also, we're going to think about y direction rotating about d. X direction force magnitude is 1600. And let's look at where D is. D is right here, right? This is our D. So if I were trying to decompose right here on the chart, that's X direction, Y direction force. And to rotating for the X direction, the moment of arm, if we draw, it's going to be this distance, right? How? Because if we decompose the force, if we extend the force, and this is going to be perpendicular distance from D to the force, and that happened to be 3. So we're going to times 3. And your D is right here. You're rotating around D. What rotation is that? That's clockwise, so that's going to be negative. So negative 4800 Newton meter. Now let's look at Y direction. Y direction, we already know it's 1200. And how about moment of arm? Moment of arm is going to be from D perpendicular to the Y direction. So that's going to be times 1. Now let's think about rotation. This force rotating about D, Y rotation, it's also clockwise, so that's negative 1200 Newton meter. Add them together, we can figure out this force 1 rotating about D, that's going to be negative 6000 Newton meter, right? So that's our last step when you add those two together. All right, let's look at one last problem. Example 6, and we're going to look at this F5, and that's 512 triangle, and this is F5, and it's 2600, and 5 it's on vertical, horizontal 12, and this hypotenuse will be 13, right? 5, 12, 13 triangle. How about we have this force rotating about K? Okay, if I would draw K relative to this force is around there. First step, we're going to decompose. We can decompose on the chart right here. The X component will be 12 because it's horizontal, so it will be 12, 13 times 2600. Cancel out. That will give us 2400 Newton. Now let's look at Y component. That's going to be 5, 13 times 2600, and that will give us 1000 Newton. Okay. Then our second step is trying to figure out this X component force rotating about K, and also our Y component of the force rotating about K. Let's look at it. X component is going this direction and K is here. And does that look familiar? This K is on this X component force. In other words, the force goes through that point. What's the moment? 0. because moment of arm is 0. It's like our example 4 here, right? Now, so we just need to worry about y component. Y component, the force is 1000 Newton here. And how about moment of arm for this direction, for this force? And if we were going up to look at on the chart, this is our y component, x component, and rotating about k, and using the grain to draw perpendicular to this force, that's going to be moment of arm as 1. Right? And now let's think about direction. This force rotating about k, y rotation, it's counterclockwise rotation. So that's going to be positive. Then the answer for that would be 1000 Newton meter. All right. Knowing that our final results for this F5 rotating about K, we know the answer now. It's going to be 0 plus 1000. The answer is 1000 Newton meter. All right. So that's all. This is a example how you solve different moment and with different forces. And we look at horizontal, vertical, slanted with angle, slanted with geometry like 3, 4, 5 or 5, 12, 13. We also look at particular case when the force goes through the point and that moment is equal to 0. So that's in a nutshell. And I'll see you next time. Bye.